The topic is coaxial capacitor. In a coaxial capacitor, the two conducting plane is of cylindrical type. In this, the two cylinders having different radius having coaxes, means both the cylinders having same axis, and one of the cylinder acquire a positive charge and another acquire a negative charge. So here this is a two coaxial conductor in which the inner conductor is charged to positive and outer conductor charged to negative. This happens when inner conductor 1 is connected to positive terminal of the battery and the outer conductor is connected to negative terminal of the battery, and there is a homogeneous dielectric in between conductor 1 and conductor 2. This coaxial conductor having a length L. Now we have to determining first the electric field intensity in this coaxial capacitor and then determine the capacitance of this coaxial capacitor. For this, we apply a Gauss's law. Here we consider the inner conductor having a radius A while the outer conductor has radius B. Now, for applying a Gauss's law, we consider a Gaussian surface. Now we consider Gaussian surface having radius rho. The value of rho is in between radius B and radius A. Now, due to the symmetrical charge distribution, the outer conductor having a negative surface charge density minus rho s and inner conductor acquire a positive surface charge density plus rho s. Now, as we know that this is a cylindrical symmetry and the direction of electric field is radially outward, that is in the direction of unit vector rho. So the electric field intensity has only rho component, that is E vector equals to E suffix rho unit vector rho, and the differential surface also having a direction that is radially outward, that is in the direction of unit vector rho. Now, what is the surface area of this conductor? The surface area of this conductor is 2 pi rho into L, because here we consider a Gaussian surface of radius rho. Now, the value of E vector and ds vector is applied in Gauss's law. According to Gauss's law, closed surface integration d dot ds is equals to charge enclosed. So in place of d we can write epsilon E. Here epsilon is used because a homogeneous dielectric material is inserted in between these two coaxial conductor. So after putting the value of E vector dot ds vector, now the dot product of E and ds vector is E rho within bracket 2 pi rho L. Now we can write in terms of E suffix rho, that is the magnitude of electric field intensity that is radially outward in the direction of rho. It is given by Q upon 2 pi epsilon rho into L. Now this is the magnitude of electric field intensity E, and in terms of vector it is written as E vector equals to Q upon 2 pi epsilon rho L unit vector rho. So this is the electric field intensity of the coaxial capacitor, and this is a cylindrical symmetry, so we use a radius of the cylinder that is rho having length L. The next is we have to determine the potential difference between these two plates. For this we use a formula that is minus integration E dot dl. Here the limit of integration is from 2 to 1 because the direction of electric field is from conductor 1 to conductor 2, and to determine the potential difference we have to move a test charge against this electric field, that is from 2 to 1. For the two conductor, second conductor, that is outer conductor having a radius b and the inner conductor having a radius a. So the limits become b to a. Now in place of E vector, we can write Q upon 2 pi epsilon rho L unit vector rho, and in place of dl we can write d rho into a rho, because dl in a cylindrical coordinate system is d rho a rho plus rho d phi unit vector phi plus dz unit vector z. Since the electric field intensity having a unit vector rho direction, then the dot product of E dot dl is also only having a rho component. Now we take a constant outside the integration. So within the integration, this integration is with respect to rho. So we can write minus q upon 2 pi epsilon L integration d rho upon rho, and the limits are b to a. Now as we know that the integration of 1 upon rho into d rho is natural log rho, ln rho, and put the value of limits here. So potential is equals to V equals to minus q upon 2 pi epsilon L within bracket ln A minus ln B. Ln is the natural log of A minus natural log of B. Now we take minus inside, it becomes within bracket natural log B minus natural log A. At last it is written as q upon 2 pi epsilon L natural log ln B upon A. Because ln A having a negative sign, so it goes to the denominator, ln B upon A. So in this way, the potential difference of the coaxial conductor is q upon 2 pi epsilon L. L is the length of this conductor, ln B upon A. From this, we can determine the capacitance of the coaxial capacitor, that is a ratio of q upon V. Now we can write it in q upon V, that is 2 pi epsilon L upon natural log ln B upon A. So in this way we can determine the capacitance of the coaxial capacitor. Now the next is spherical capacitor. In spherical capacitor, two spherical conductors are placed which having a same center. Since it is a spherical symmetry, so here we take the radius of the sphere is r, because r, theta and phi are the coordinates of the spherical coordinate system. So here we take a radius r. Now the inner sphere having a radius a, while the outer sphere having a radius b. The inner sphere having a positive charge on its surface, while the outer sphere having a negative charge on its surface. This happens when inner sphere is connected by positive terminal of the battery and outer sphere is connected by negative terminal of the battery. And in between sphere 1 and 2 there is a homogeneous dielectric having permittivity epsilon, that is epsilon equals to epsilon not epsilon r. Now to determine the electric field intensity and then capacitance, we assume a Gaussian spherical surface. We have to apply a Gauss's law. So we apply a Gaussian surface which having a radius r, because the inner sphere having a radius a and outer having a b. So we assume a spherical Gaussian surface that is of spherical type. Its radius is r. We assume it r. That r is in between radius b and radius a. That is r is greater than a but less than b. Now we apply a Gauss's law. Gauss's law is closed surface integration d dot ds is equals to q enclosed. Here d is equals to epsilon e. Now again we have to determining the dot product of E vector dot ds vector. Now this is a spherical symmetry. The electric field is radially outward here. So the electric field intensity E having a R component. So it can be written as ER unit vector R. And for ds vector, that is a differential surface, the surface area of a sphere is 4 pi r square. 4 pi r square is the surface area of the Gaussian spherical surface. So in place of ds vector we can write 4 pi r square unit vector r. After taking a dot product we get only r component. So it becomes epsilon E suffix r 4 pi r square equals to q. So in terms of E having r component, ER equals to q upon 4 pi epsilon r square. Here epsilon is the permittivity of the dielectric. And in magnitude form, electric field intensity E equals to q upon 4 pi epsilon r square unit vector r. Now we have to determine the potential difference between two spherical conductors. For this, we move a test charge against the electric field, that is from second conductor to first conductor. Both are spherical one. So potential difference is equals to minus integration E dot dl, and the limit is from 2 to 1, that is against the electric field. Now for 2 the radius is B, and for 1 the radius is A. So the limit become B to A. In place of electric field E, we can write q upon 4 pi epsilon r square unit vector r, and for dl we write dr unit vector r, because differential length dl in spherical coordinate system is dr unit vector r plus r d theta unit vector theta plus r sin theta d phi unit vector phi. Since the electric field intensity having the r component, so the dot product of these two is having only r component. So in place of dl vector we can write dr unit vector r. Now we take a constant part outside this integration, that is minus q upon 4 pi epsilon is the constant, and integration of dr upon r square, and the limit is from b to a. The integration of 1 upon r square is minus 1 upon r with limits b to a. Now after putting the values of limit in place of r, we get q upon 4 pi epsilon within bracket 1 upon a minus 1 upon b. So this is a potential difference of the spherical conductor, and from this we can determine the capacitance of the spherical conductor, that is the ratio of q upon v. So we can write it in terms of q upon v, that is equals to 4 pi epsilon upon within bracket 1 upon a minus 1 upon b. So this is a capacitance of the spherical capacitor. Now there is a case when we consider b tends to infinity. B tends to infinity means the outer conductor having a radius of infinity. When the outer radius is infinity, we can say that the outer sphere is of infinite dimensions. So from the assumption we means that the outer sphere having radius infinite, so we can say that V remains only a inner conductor, inner spherical conductor, that is called isolated sphere. It is act as a conducting body only. So when we consider b tends to infinity, the inner conductor act as a isolated sphere. Now put the value of b equals to infinity here. So 1 upon b equals to 0. So we get the capacitance of this isolated sphere is 4 pi epsilon a. So this is a special case of the isolated sphere that is obtained from spherical capacitor by making the outer spherical conductor radius to be infinity. Now there is some important points about capacitance. When the two capacitors connected in series, here C1 and C2 are the capacitor connected in series, so the resultant capacitance of this combination is 1 upon C equals to 1 upon C1 plus 1 upon C2, or we can also determine the equivalent capacitance C equals to C1 C2 upon C1 plus C2. So when the two capacitance or three capacitance are connected in series, so we use the equivalent capacitance in terms of C1 C2 upon C1 plus C2. Now when the two capacitance are connected in parallel, in this case the equivalent capacitance is C1 plus C2. We can say that it is just opposite of the resistance. Series resistance are added, but here this parallel capacitance are added. Now second point is resistance. R is equals to V upon I. This formula is used when the dimensions, the specifications is uniform. For non-uniform specification we use a integration. So in place of V we can write E dot dl, line integration E dot dl. Here the negative sign is neglected because we are interested in absolute value of the potential. And in place of I we can write surface integration J dot ds. Now we know that J equals to sigma E, that is a point form of Ohm's law. So in this case we can determining R, that is the resistance. Capacitance C is equals to Q upon V. Q can be determining from the Gauss's law, that is closed surface integration D dot ds, and again the potential V is line integration E dot dl. Here also the negative sign is neglected as the potential is absolute potential. Now in place of D we can write epsilon E. Now these are the formula to determine the resistance and capacitance. When the dimensions are non-uniform, then we use an integrations formula. Now from here we determine the constant, that is called time constant. Time constant is RC time constant. So when we multiply R and C, we get Q upon I. Q upon I, V is cancelled here, RC. And from non-uniform formula, that is from the integration formula, we get epsilon upon sigma. This is only for homogeneous medium. Means for the homogeneous medium we can determine the time constant, that is equals to epsilon upon sigma. This time constant is denoted by T suffix R, and this is called relaxation time of the medium separating the conductors. So this is called a time constant RC, that is epsilon upon sigma. Now for parallel plate capacitor, the capacitance is epsilon S upon D. S is the area of the plates and D is the distance between these two plates. R is equals to D upon sigma S. This resistance can be obtained by using time constant RC equals to epsilon upon sigma. So in place of C we can write epsilon S upon D, and from here we can determine resistance, that is D upon sigma S. Here resistance is equals to L upon sigma S. L is the length of the conductor and S is the area of cross-sectional area. Now for a cylindrical capacitor, the capacitance is 2 pi epsilon L upon natural log ln V upon A. So similarly we can determine R by using epsilon upon C sigma. And for spherical capacitor, the capacitance is 4 pi epsilon upon within bracket 1 upon A minus 1 upon B. For a spherical capacitor, we can also determine the resistance by using a relation that is R equals to epsilon upon C sigma. Now, the sixth point is isolated spherical conductor. Isolated spherical conductor can be obtained by making the outer spherical conductor and whose radius tends towards infinity. Then we get an isolated spherical conductor and its capacitance is 4 pi epsilon A. Now for this the resistance is equals to 1 upon 4 pi sigma A. That is obtained by using R equals to epsilon upon C sigma. Here we note one point. Sigma is the conductivity of the dielectric medium that is separating the two plates, and the resistance R, that R is not the resistance of the capacitor plate, but R is the resistance that is called leakage resistance between the plates. So these are the some important points about capacitance.